Good morning, everyone. I'm Dinesh, and along with my teammates Manas, Omsing, and Ravi, we'll be presenting our topic virtual memory, cost, and performance. This topic is an important part of computer organization and architecture. It helps us to understand how computers manage memory efficiently. So let's begin by understanding what virtual memory means and how it actually works. So virtual memory is a main memory management technique that makes your computer feel like it has more random access memory than it really has. Its usage are part of the secondary storage like hard disk or SSD as an extension of main memory. So even if the RAM is full, the programs can still run smoothly because the system temporarily stores extra data on the disk. This process is managed by both hardware called the memory management unit and the software which is the operating system. In short, virtual memory allows large applications to run on small physical memory by using the disk as extra space. So let's see how virtual memory works. When a program runs, it uses virtual addresses instead of physical memory locations. The memory management unit converts these virtual addresses into physical addresses that points to actual locations in RAM. So if the system runs out of the RAM, it uses a part of the hard disk or SSD as extra memory space. This lets larger programs run even when the physical memory is small. So this diagram compares two situations. At the top, without virtual memory, the system only has 10 MB of RAM, so it's limited to that capacity. At the bottom with virtual memory, the same system uses 10 MB of RAM plus 490 MB of hard drive space, giving it the ability to handle up to 500 MB worth of data. So even though the computer physically has only 10 MB of RAM, it acts like it has much more memory available. So this is how virtual memory extends usable memory and allow better multitasking.
My name is Manas Pandya, and today I'm going to talk about the two ways computers manage memory: paging and segmentation. First, paging. Paging is like having a bookshelf where every shelf is exactly the same size. Memory gets divided into fixed chunks, usually 4 KB or 8 KB. The cool thing, it is super simple for hardware to manage, and you never get awkward gaps between blocks. The downside, you might waste a little space inside each page if your data doesn't fill it completely. Segmentation. Segmentation is more like organizing your closet by category: shirts, pants, shoes. Each section can be of different sizes. It divides memory based on logical parts like code, data, stack, and heap. This makes sense to programmers because it matches how we think about programs. But because segments are different sizes, you can end up with gaps in memory that are too small to use. Now let's talk about why we use virtual memory and what problems it causes. The advantages. First, you can run way more programs at once. Ever wonder how your laptop runs Chrome with 50 tabs, Spotify, Word, and more with just 8 GB of RAM? That's virtual memory working its magic. It's also cost effective. You don't need expensive RAM upgrades because the OS uses hard drives space as extra memory. It keeps things stable and secure. Each program gets its own private memory space, so crashes don't spread and apps can't peek at each other's data. Plus, it's smart. It only loads the parts of a program you're actually using, not the whole thing. Now, let's talk about the limitations. But there's a catch, right? RAM is fast, but hard drives are way slow. When your computer needs to grab something from disk instead of RAM, you'll really notice the slowdown. Then there's trashing. When your computer swaps stuff between RAM and disk so frantically it can barely do actual work, everything becomes super slow. All this swapping wears out a hard drive and especially SSDs which have limited write cycles. The operating system has to track everything: what's in RAM, what's on disk, and that takes processing power. And if power fails during a swap, you could lose data. So virtual memory is super useful, but it's all about trade-offs. We sacrifice some speed for the ability to do more with less RAM. Thank you.
I am Ravi Kumar Gupta. I am be explaining the cost efficiency of a virtual memory. Virtual memory help reduces hardware cost while maintaining the performance of a computer. Instead of adding more physical RAM, the system uses part of a SSD HDD as extra memory, thus make low cost alternative to RAM expansion. If we look at to the graph on the slide, we can see that the RAM is more expensive while SSD and HDD are much cheaper than RAM. Because using this as storage as virtual memory become a cost-effective solution for running a heavy application even for a low-end systems. It is especially helpful for a budget laptop, PC, and embedded systems as it allows them to perform tasks normally require more RAM. For example, upgrading a 8 GB of a RAM costs around 2500 to 3000, but using 8 GB of a disk space for virtual memory costs around nothing extra. However, there is always a trade-off. It's cheaper but slower than physical RAM, so we can say that virtual memory is cost efficient, but it's slightly compromised on a speed. Now we are moving on the performance analysis. Nice. Performance analysis of a virtual memory. Now let's move on the performance analysis of a virtual memory. The performance of a virtual memory depends on how it used and how the system is configured. Talking about the positive aspect, virtual memory allows systems to run multiple programs at once and prevents out of memory error. It also ensures that the system stability and with SSD, the swapping process is much more faster than before. However, there is something negative aspect also. The main issue is speed. Disk access is much more slower than the RAM. To give an idea, RAM work in nanoseconds, and while disk access take milliseconds, which means the disk is 10,000 times slower. Because of this, frequent paging can increase CPU waiting time and cause crashing, where the system spends more time swapping data to the real work. A high number of a page fault can slow down the system overall performance. So in conclusion, virtual memory improves multitasking and stability, but if not managed properly, it can also reduces speed and responsiveness. Thank you for listening. Now I'd like to have take over to the Om Singh, who will continue to the next topic. Thank you.
Hi, my name is Om, and I will now continue our presentation by discussing the optimization techniques, real world applications, and our conclusion of virtual memory. Building on the previous explanation of the cost performance trade off, a big question comes up. How do we mitigate the performance limitations of virtual memory? The answer lies in a broad and layered approach to the system design, which I'll detail with direct reference to our slides. As outlined, several key strategies are employed to minimize the performance penalty. First one would be to use SSDs instead of HDDs because they drastically improve virtual memory performance by reducing disk latency and increased transfer speeds. This shortens page fault service times and makes swapping smoother and less disruptive. We can also increase physical RAM. Adding more physical RAM expands the fastest level of memory, which reduces the dependency on virtual memory. This minimizes page faults, lowers disk input and output, and improves overall system responsiveness. Also, applying efficient page replacement algorithms like least recently used, first in, first out, or optimal helps the operating system retain frequently used pages in RAM. This reduces page fault rates and enhances the effective access time of the system. Also, manually tuning the page file by setting a fixed size or moving it to a faster drive can improve consistency and performance in high demand workloads. This gives user finer control compared to the automatic OS management. Moving to the application of virtual memory, a prime example as highlighted in our PPT is its implementation in Microsoft Windows through the pagefile.system file. This is a hidden system file that serves as the reserve space for paging. When physical RAM is fully utilized, the Windows Memory Manager automatically transfers inactive memory pages to this file on disk. This mechanism is what prevents system crashes due to out-of-memory errors and enables the smooth operation of multiple heavy applications such as having dozens of browser tabs open alongside other software, even on systems with limited RAM. The stability and scalability provided are direct benefits of the virtual memory management. In summary, virtual memory is a powerful architectural technique that creates an abstraction layer, extending usable memory capacity by leveraging secondary storage. It also provides a cost-effective and scalable solution for enabling robust multitasking and supporting large applications. While inherent performance trade-offs exist due to speed disparity between RAM and disk, these can be effectively minimized through the optimization techniques we have covered. In simple terms, virtual memory shows how smart design can overcome hardware limits. It keeps our system fast, stable, and capable of handling more than they physically can. And it is a very important part of making systems of today and tomorrow. Thank you. This concludes our presentation.